the holdup is.
Modern agriculture usually hides behind a pastoral myth of sunrises and soil. But here, on the edge of the tropics, the reality is aggressive. This isn't farming. This is a siege. A convoy of 50 heavy-duty haulers forms a diesel-chugging snake stretching a full mile, kicking up red laterite dust. Their payload is singular, massive, and ticking like a biological time bomb. 1 million cassava roots. This monolithic delivery represents exactly 24 hours of production for the facility waiting at the end of the road. It is a high-stakes race. Once pulled from the earth, the cassava root begins a rapid enzymatic decay. Within 48 hours, the starch inside, the prize we are hunting, begins to ferment. If this convoy stops or the intake bay jams for more than 30 minutes, the payload rots. A delay here means a $500,000 loss in a single shift. But rotting isn't the only danger. Hidden inside the cellular matrix of every tuber is a chemical defense mechanism evolved over millennia. Cyanogenic glucosides, in plain English, cyanide. To transform this poisonous, dirt-caked tuber into the pristine pearls in your bubble tea or the binding agent in your ibuprofen, engineers designed a machine of terrifying complexity. It must ingest 50 tons of raw material every 60 minutes, scrubbing out a lethal toxin while extracting a microscopic granule that hates to be released. The harvester is a hydraulic beast, gripping the root crown with 20,000 pounds of lift force. Speed is the primary directive. Conveyors strip the foliage, leaving only the starch-rich tuber. No time for inspection. Harvesters fill hoppers, hoppers fill trucks, and trucks race the clock. As the convoy breaches the processing zone perimeter, the scale becomes clear. This is not a kitchen. It is a chemical refinery disguised as a food plant. The goal is absolute. Turn 1 million poisonous roots into 500 tons of white gold before the sun comes up. The first truck backs into the intake bay. The hydraulic bed lifts. The avalanche begins. The machine is hungry. As raw tonnage hits the intake hopper, the first great enemy reveals itself. Not cyanide, not rot. Silica, sand. Roots arrive encased in a concrete-like armor of dried mud. For the delicate surgical steel blades inside, this soil is fatal. If even a fraction of a percent of this abrasive grit enters the high-speed rasping phase, it acts like 80 grit sandpaper, chewing through $50,000 of precision tooling in a week. The war on sand starts in the dry sieve, a rotating 16-foot cage turning slowly. A brute force gravity filter where tumbling roots shed loose dirt through grate bars. Boulders and debris fall away, but stubborn clay remains. To strip the skin, roots drop into the paddle washer. Think industrial exfoliation on a geological scale. A long, water-filled trough houses a massive central shaft, armed with heavy steel paddles that don't just stir, they agitate with violence. The physics rely on root-on-root friction. Paddles churn the 50-ton load, forcing tubers to collide and grind in a chaotic tumble where water turns to black sludge. Technicians monitor the turbidity of this dark effluent, carrying away tons of dissolved clay. But simple tumbling isn't enough. The roots enter the cleaning gauntlet's final stage, the high-pressure spray tunnel. Nozzles blast tumbling roots with recycled water at 145 psi. The white glove test. Jets target crevices, blasting away final silica grains. This hydropressure decontamination has a secondary function, peeling. The corky skin contains the highest cyanide concentration. Friction and water jets flay this layer, removing 20% of the toxin load before the root enters the building. The conveyor elevating roots out of the washer reveals a transformation. Dirt-encrusted tubers are now gleaming, pink-skinned cylinders. They look harmless? They are not. Before the main event, a heavy-duty rotary cutter slices erratic 2-foot tubers into uniform chunks, ensuring a consistent feed rate. The conveyor climbs, carrying chopped root toward the roof. Noise rises. The floor vibrates. We approach the heart of the beast. Cleaning is over. Violence begins. Crossing the threshold into the extraction zone, the air turns humid, smelling of raw vegetable matter and ozone. But the dominant sensation is a high-pitched scream penetrating industrial ear protection. The Rasper, specifically the Larson JCR, the apex predator of the starch world. To understand this machine, you must understand the root's microscopic architecture. Starch granules are tiny, 1/10 the width of a human hair, locked inside tough cell walls reinforced with cellulose. Crushing isn't enough. To get the yield the market demands, you must explode the cells, a cellular jailbreak. The Rasper achieves this through kinetic fury. A stainless steel rotor spins at 2200 RPM. The drum is lined with hundreds of saw-toothed blades of hardened tool steel. At full throttle, blade tip speed hits 328 feet per second. Commercial jetliner takeoff speeds contained in a steel box the size of a closet. Chopped cassava drops directly onto this spinning rotor. Physics turn catastrophic. Roots jam between the screaming rotor and a static file block housing. The gap set to a tolerance of less than the width of a dime. Upon impact, the root doesn't break. It vaporizes. Shear force ruptures cell walls instantly, releasing starch granules into a liquid suspension. Rasping specialists watch motor amp loads with obsession. A spike, it ends dull files. Dull blades mash cells instead of rupturing them. Mashing means trapped starch. Trapped starch means lost money. Maintenance is a ritual of precision. Every few shifts, the line pauses to swap battle-scarred blades with surgical speed. A dull blade costs $10,000 in lost yield in a day. Output is now a coarse slurry, liberated starch, water, cyanide, and millions of tiny fibers. This slurry pumps immediately to extraction. The enemy here is fiber. The Rasper worked too well, mixing valuable product with woody debris. If fiber remains, the starch is gritty. The gatekeeper is the centrifugal sieve, operating like a high-G washing machine. Slurry enters a conical basket lined with precision stainless mesh. Rotating paddles spin at high velocity, generating centrifugal force that pins the mixture against the screen. Size dictates separation. Microscopic starch milk forces through the mesh. Larger fibers trigger a trap caught inside. Angled paddles scrape this wet fiber cake across the screen, driving it forward until ejection. A violent, rhythmic slap, slap, slap beats pulp against steel walls. What emerges underneath is a milky white liquid looking like heavy cream. But appearances deceive. This chemical cocktail is full of proteins, fats, and enough cyanide to kill a human. Solid waste is gone, but invisible poisons remain. Refining must move from the mechanical to the molecular. The liquid flowing through these stainless arteries is raw starch milk. White, opaque, and chemically hostile. Primary contaminants: fruit water, soluble latex proteins, and cyanogens. Mesh screens can't filter liquid poison. Engineers must exploit density using the Hydrocyclone array. Resembling a futuristic server room, racks hold hundreds of plastic cones in circular clusters. No moving parts, no motors, only fluid dynamics and crushing pressure. Starch milk pumps into these cones at 115 psi, entering tangentially to create an artificial hurricane, a vortex of immense power. This is the gravity-defying corkscrew. Starch granules are denser than water and cyanide. Centrifugal force throws heavy starch outward against the cone wall. sliding down to exit in a concentrated stream. Lighter elements, water carrying cyanide and latex, catch in a secondary inner vortex, spiraling upward against gravity. Down goes the product. Up goes the poison. A single pass fails. Fluid must travel a 12-stage cascade, a washing line of cyclonic violence. Stage 1, toxic. Stage 12, crystal clear. Control room technicians monitor pressure differentials. A drop means a clogged cone and separation failure. If the balance tips, the yellow tornado of latex proteins collapses into the white starch, ruining the batch. The room shifts sensorially. No roar, just the continuous high-pressure hiss of fluid rushing through plastic like 1,000 snakes. Pipes sweat cold condensation. Sampling raw milk before hydrocyclones is a mistake made once. Acrid, bitter, burning the tongue. A biological alarm screaming poison. But at the 12th stage outlet, cyanide levels drop to safe trace amounts. Latex gone. Fruit water flushed. A pure suspension of starch and fresh water remains. But the product is drowning. 60% water. To ship it, we need powder. Boiling off this water requires a power plant's worth of energy. We need a mechanical strip, and we need it in seconds. The slurry arrives at the dewatering station for drastic reduction. Liquid to solid, no heat. The hero is the peeler centrifuge, a reverse potter's wheel. A massive horizontal drum, lined with filter cloth, spins up to 1,000 Gs. Water rips out, draining away, while starch granules trap inside. Transformation occurs. Loose liquid becomes a solid cake, compressed against basket walls into a rock-hard ring of white matter. Then, the hydraulic shave. With the drum spinning at full velocity, a robotic arm drives a hardened steel knife into the basket, the peeler. A mechanical whine shifts to a grinding shriek as steel bites into hard starch. The blade harvests ribbons, peeling the cake away. Moist ribbons collapse into a screw conveyor. Moisture drops to 35%. Mechanical limits reached. You cannot squeeze more blood from this stone, but 35% is still too wet. To prevent mold and reach the 12% spec, we introduce the factory's most dangerous element, fire. But starch has a weakness. Heat it wet, and it gelatinizes into tapioca pudding, clogging pipes and shutting down the facility. We need to dry it faster than it can cook. We need a vertical inferno. Rising 6 stories above the floor, the flash dryer dominates the final tower with stainless ducts and cyclones. At the base, a massive natural gas furnace roars, heating filtered air to 320 degrees Fahrenheit. Jet engine-sized intake fans accelerate the superheated air to 65 feet per second. A deafening roar drowns all speech. Wet starch ribbons feed into a disintegrator fan, pulverized into a fine mist, and blasted directly into the vertical column of fire. The thermal skydive. Flash drying races against time. Suspended in the hot stream, the massive surface area of tiny particles transfers heat instantly, flashing water to steam. This violent evaporation cools the air around the particle, protecting the granule from burning. Residence time inside the pipe, less than 3 seconds. Moisture plummets from 35 to 12%. Powder travels up the 6-story column on a thermal updraft, a reverse blizzard swirling through the viewing glass. At the top, dry fluffy powder swirls down cyclones while moist air vents. An automated logic controller modulates gas valves thousands of times a minute. A 10-degree fluctuation could leave powder wet or scorched. At the bottom rotary airlock, the product falls cool, snow white and bone dry. Following the product to the packaging line, the dryer's roar fades to the rhythmic hiss-clunk of bagging automatons. Starch is weighed with digital precision into 55-pound sacks, sealed and robotically stacked. Final quality check. Cyanide, undetectable. Fiber waste, pumped to a biogas reactor to ferment methane, firing the boilers that heat the flash dryer. The waste powers the machine that created it. Outside, the sun sets. The truck convoy is gone. The mountain of 1 million roots vanished, eaten by the machine. In its place, 500 tons of pure tapioca starch sit ready for global shipment. A triumph of industrial engineering taking a poisonous, dirty root and disciplining it into a vital commodity. The machine doesn't sleep. Another convoy is on the horizon. The cycle begins again,